Best announcement ever. It's crazy. So, hey, very nice that you're all here. It's not full. I did not expect this because I'm talking about compiler stuff, right? So, first of all, my name is Chris. I work for a tiny little company that's on my shirt. You might know it. And that brings me, it's unfortunately the last day. I'd like to have my talk on the first day because I'm asking the most important question of the conference usually. And the question is, who in here has a Twitter account? That's actually not bad for Poland because I heard you guys don't really use Twitter. So I want you to you might have seen the small displays outside. They have tweet walls on them. So if you're tweeting with the hashtag Devoxx Poland, then they'll show up on the tweet wall and everything. And I want you to tweet about all the conferences that you attended, the sessions, the sessions you attended, the sessions you liked, what you liked about them. Maybe don't tweet if you didn't like them, you know. We have feelings too. And so do that. And if you're going to tweet about my talk, add the hashtag TwitterVMteam because we actually have a VM team. And we are not that small anymore. I think we're 8 people now. We just got a bunch of interns over the summer, so we have a couple more people working on different things. We have 3 GC engineers, and the GC engineers usually take care of all the GC problems that everyone has, and so do we. Then I'm a compiler engineer. I work on compiler stuff. That's the fun stuff. And a colleague of mine, he's helping out writing Scala-specific optimizations for Graal. And then we have a bunch of other people working on infrastructure things. We build our own JDK, so we have to do that. And then an intern right now is working on a tool called AUTOTUNE. And AUTOTUNE is actually what I'm going to talk about today. All right, so a little bit about me. I'm working on JVMs for a very long time. I think it's 15 years now even. And all these 15 years, I was working on JIT compilers. So I'm going to ask you a bunch of questions because I want to know what you know. And put your arms up. Who knows what a JVM is? Well, I'm hoping everyone does. Yes, okay, good. Who knows what a JIT compiler is? Yeah, quite a few. So, but I'll briefly explain it. So if you compile your Java Scala closure or whatever to Java bytecode and then run it on the JVM, you first interpret the code in the interpreter, which is really slow, and then we have something called JIT compilers, just-in-time compilers, who compile the code while you run it in the JVM into native code so that we run faster. So that's what a JIT compiler is. I work on that stuff. I used to work at Sun and Oracle, and in the Hotspot compiler team, mostly working on C2. Who knows what C1 and C2 are? Okay, not many. So you guys know what Hotspot is. Yes, Hotspot, the JVM of OpenJDK, good. So Hotspot has 2 JIT compilers. One is called C1 or client compiler, and the other one is called C2 or server compiler. You might remember, the older people of us might remember the dash client, dash server thing we used to use many, many years ago. You don't need that anymore. So C1, the purpose of C1, it's a high throughput compiler. So the purpose is to get away from interpreting code as quickly as we can. It doesn't do a lot of optimizations. There's some inlining, there's some other optimizations, but nothing too crazy because we want to run on native code as quickly as we can. And then C2 is a highly optimizing compiler. It uses all the optimization tricks that are available, you know, way more inlining, escape analysis, loop unrolling, auto-vectorization, you know, all that stuff. And then that's the code that you actually then run your application on with peak performance. So I used to work on C2. Then these 3 projects were basically the biggest ones that we've done, or that I've worked on at my time at Sun and Oracle. JSR 292, some people might know it's Invoke Dynamic, support for dynamic languages. If you're using Java 8 lambdas, you're actually using Invoke Dynamic under the hood. That's how it's implemented. You might not know that. There were 2 implementations of Invoke Dynamic and method handles. The first one was a lot of handwritten assembly code. So that was, first of all, a major pain to write, but even a bigger pain to maintain because we had to port it to all the different architectures we supported. So that was a lot. Then SAP had to port it to all the architectures they supported, which was like 10 or something. So, and then on top of it, we had a performance issue. So we decided to completely redesign the thing and move all the handwritten assembly logic into Java, into a package called Java Lang Invoke. And a lot of the Java code in Java Lang Invoke I wrote, so if it doesn't work, you could technically blame me. But I always say my code was completely fine, and the people who touched it after me, they broke it. JEP 243, Java level JVM compile interface, also called JVM CI, we introduced that in JDK 9. And it's basically, people know what Graal is? Not Graal VM, Graal. So the difference between Graal VM, you all might know Graal VM, and it's basically, it's an umbrella term for 3 different technologies. It's Graal, the JIT compiler. Who knows what a JIT compiler is? I just explained it. All the hands should be up. Truffle, which is a framework to implement language runtimes, and then Substrate VM, which you might know under the name of native image. And I'm only talking about Graal, the JIT compiler. All right? So Graal is written in Java. And so it has to talk to the JVM because the JVM is written in C++. There's an interface that Graal was using. And basically what we did is we took the interface, extracted it, and put it in a Java module in JDK 9. And the main reason we did this was for JEP 295, ahead of time compilation. This is not native image. That's different. This is a small command line utility where you can pass in class files or jar files, and then it compiles, sends all the methods over to Graal, Graal compiles it, and then it spits out a shared library at the other end. And then Hotspot, when it starts up and it finds shared libraries, it can pick them up, and you're basically skipping interpreting code. It might help if you have a big application that runs a lot of code when it starts up. It might help with startup. I now work at Twitter, best company on the planet. You should tweet about that I said this. This is Twitter. That's what Twitter looks like. We have, at least in 2016, it's probably bigger now, we have hundreds of microservices, right? And then we have thousands of instances of these microservices, and on top of it, we run on heterogeneous hardware, like pretty much everyone does. We own our own data centers, so we own our own hardware. We know what machines we're running on. You probably run in the cloud. You have no clue what hardware you're running on, right? So, but keep that in mind. Heterogeneous hardware is important for performance tuning. Performance tuning in general is hand tuning doesn't scale, right? Performance tuning as it works today is pretty much you sit at work, you get annoyed with the performance of one of your things, and then you decide to tune it, right? And that happens every 3 years, 5 years, never, right? So that's the issue. And then if you decide to tune it, you can only manage a few parameters, right? Because you have to build up a mental model in your head to understand if I change this parameter, this is going to happen, and so on and so on. And then you have to decide what to do next. It's very time-consuming, labor-intensive, error-prone. The last point is the most important one. Upgrades make optimality fleeting, right? We all live in this super agile world. You deploy 100 million times a day because it's cool. We deploy a couple times a week, so we are kind of in the same boat. But the code is constantly changing, right? So if you tune for today's code, it's not optimal tomorrow anymore because your code changed. So many services all around the world, including Twitter services, operate below optimality. It's absolutely true. So performance tuning is a little bit of a theoretical part of performance tuning. It's what it does, or what you want to do, is you have a function defined over domain X, and then you want to find a configuration A that maximizes F, whatever F is, right? It could be anything. It could be reduce CPU utilization, or reduce memory consumption, increase throughput, you name it. And then, very important, your configuration A is always subject to a constraint, right? And the number one most important constraint is it still has to work. And you will see later when I show the experiments that I did with our services that you can actually tune too far so that the service doesn't work anymore. You violate some of the constraints. This is performance tuning, basically what it looks like. You pick a parameter, then you run it on the system, whatever that is, right? You measure your F, and then you get it back, and then a performance engineer, a human, a person, you, looks at the value that you got back, and then you have to decide, was it better or worse than before? And from that on, you pick the next value for your parameter to test. So, and then a performance engineer doing this is very, very expensive, right? I mean, maybe we could get a monkey to do it, I don't know, but what we really want is some black box, right? Something that does that for us. We don't even care what this is, we only want, based on the measurement, the input that we got, what to try next. And we at Twitter use for this black box something called Bayesian optimization. Some of you might have heard of it. It's a method to learn potentially noisy, yes, objective functions iteratively efficiently. That's important because you need, if you do a performance tuning experiment, you want it to finish rather quickly, right? You don't want to wait 2 months because, as I said earlier, your code is constantly changing, right? You can't run an experiment for that long. So it finds new optima in a few iterations, absolutely works well with nonlinear, multimodal, high-dimensional functions. That's important because the JVM has hundreds of parameters you could tune, right? We don't only want to tune like one, we want to tune many of them so we get the maximum performance out of it. So if you want to know more about how this Bayesian optimization thing works, and I really don't know, then you should watch one of my colleagues' talk, Rumke's talk, one at Devoxx about 2 years ago, where he explains all the Bayesian optimization. He has a very soothing voice, so watch it at home. And then you see the slides he's using, the graphs. Basically what I did, I stole them. That's all I did. That's what I do at Twitter. So I'm going to explain to you very quickly and I'm not an expert in Bayesian optimization. So if you know, don't ask questions, because I can't answer them. This is just for you to understand the data and the graphs we're seeing later better. Okay, so we're looking at one parameter. It goes from -6 to 6, and then on the y-axis we have performance and highest better. And the 3 data points you see are actual evaluations that we ran, so these are true values. And this is the actual performance curve, which we don't know, right? So what Bayesian optimization does, it assumes a performance curve that looks like this, and then you see the blue area above and below the curve, that's the uncertainty. And you see where we actually have a data point, the uncertainty is 0 because we know that's a correct value, all right? Overlaid with the actual performance curve looks like that. It's not really the same, but that doesn't matter, right? Because we'll figure it out as we go. So the next thing you do, what Bayesian optimization does, it puts in a line at your best result, right? And then the blue part above the red line is the graph at the bottom, the expected improvement. So the more blue you have, the more improvement you are expecting. And that's where Bayesian optimization tries next. So you see the second one from the left, that's the data point we try next. So we run that experiment, we get that result, and we try the one in the middle, we get that one, then the one on the left, looks like this, and then that one. And then we've exploited the space down here, right? And as you can see, we find out what the actual performance curve is. And then we go to the next one, which is the one over here on the right. So we try that one. That was not very good, okay, so we go somewhere else. We go to the very left. Try this one, also not very good, so we go over to the right. Try this one, yes, better, this. And we found the global optimum. That's what Bayesian optimization does for us. It's basically what you would do as a human as well. But this is so much better, faster, and cheaper, right? That's all we need. We just need the black box to tell us which value to try next for our parameter. So we like Bayesian optimization because it's non-parametric, robust, extensible, battle-tested on many types of real-world high-impact problems. That the last point is important to us because we have hundreds of services, right? We are not quite there yet, but the ultimate goal of this AUTOTUNE tool is that it's always on in production, that services tune themselves constantly. And we need to trust it, right? All the experiments I'm going to show you today, I was supervising and taking care of them, that they're actually really correct and everything. But if we are tuning hundreds of them at the same time, we cannot possibly look at all of them, right? We have to trust what the Bayesian optimization does for us. Okay, that was it. Experiments. So now it's the important and interesting part. So what is AUTOTUNE? I call it a BOAS, It's a Bayesian optimization as a service. At every conference, I try to get this hashtag trending. Never works. I'm not sure. People are not interested in hashtags. So it's basically, we acquired a company a few years ago called WetLab. And WetLab is basically an enhancement of a framework called Spearmint. And Spearmint is still available open source. Just the one we have is slightly better. And that runs as a service inside of Twitter. And other tools or whatever use that Bayesian optimization service as well. So we just use that one. And AUTOTUNE is really only, you can think of it as a more complicated script that starts and stops services, instances, test runs. That's really all it does. It's a driver to run experiments. We run in Aurora on Mesos, whatever, but if we ever would open source AUTOTUNE, and we will, but now it's unusable, basically, someone would have to write, I call it a back-end, to start and stop instances. For if you run on Kubernetes, you would have to need something that starts and stops Kubernetes instances and things like that, right? So that's really all AUTOTUNE does. It runs something, then you measure your metric, and then AUTOTUNE takes the metric, sends it over to the Bayesian optimization part, and then get a return, an answer back. That's all it does. Sounds easy, is not. Because if you need that to run in your data center, nothing's ever easy. So what is Graal? We kind of talked about this already. It's a Java virtual machine just-in-time compiler, actively developed by Oracle Labs. There was a talk, at least today, and I think even the last couple of days, Red Hat was talking about Quarkus and everything, so you might have seen that already. There's an official OpenJDK project, actually, but all the work's done on GitHub. Uses JVM CI, we talked about this already, and it's written in Java. It's not important for this talk that it's written in Java, but if you are planning to try Graal, and I would really, really encourage you to do it, you might want to watch this talk, how to use the new JVM chip compiler in real life, where I do a lot of demos to show you if you are running on JDK 11, let's say, and I'm sure everyone in here is running on 11 in production. Yes? That's what I thought. We are running on 8, so we're in the same boat. But if you're running on 11, there is Graal in JDK 11, in OpenJDK 11. If you turn it on, the state today is we are not AOT compiling Graal in OpenJDK. So there's something called bootstrapping, because basically the JIT compiler is just another Java application in your JVM, but when you run it, it kind of has to compile itself, right? So it's a metacircular thingy, and you have to know that. It increases startup of things slightly, but it's usually in the noise, so don't worry about it. And then the other thing you should know, if you're running benchmarks or anything, Graal is allocating memory, because it's in Java, it's allocating memory for compilations on the Java heap, while C1 and C2, which are written in C++, are allocating memory with malloc on the native heap. It's just a thing to know. And then Oracle Labs with Oracle, the Java Platform Group, are working together on a project called libgraal, where we use native image to AOT compile Graal and link it into the JVM. I think the latest Graal VM binaries, images you can download actually do that already. But if you're using OpenJDK 11, this might be interesting. Okay, so which parameters did we tune, or did I tune? I picked 3 inlining-related parameters. Who knows what inlining is? Right? So inlining is in your code. Sometimes you have snippets of code that are repeating, right? And you are a very good engineer and software designer. So basically what you do is you take that code, put it in a method, and call it from all the places. Very good from a maintenance perspective. From a performance perspective, not so much, right? So what the compiler does, it undoes what you did. It basically takes the code again and puts it back to the call sites. The reason we do this is if we inline, our worldview of what we are compiling gets bigger. And the more we know, the more optimizations we can apply. And one of them, which is very important, is escape analysis. And escape analysis, I'm not going too much into detail, but it's basically getting rid, it can eliminate object allocations if the compiler can prove they are not required. And the more you know, the more objects you can eliminate. So inlining, very important. I tuned these. The first one is called trivial inlining size, and the default value is 10, and it's basically 10 nodes in the compiler graph. So the way compilers work, they parse source language, could be, I don't know, C++, or in our case it's Java bytecode, so we parse that into graphs, into compiler graphs. And if that graph has less than 10 nodes, we know it's a very trivial method and we just inline it all the time. So we're not looking at any profiling data or anything. The second one, maximum inlining size, is basically the other end of the spectrum. If it has more than 300 nodes, we don't inline it. And then the third one is very similar to the second one. It's called small compiled low-level graph size. It's also the default 300. And the most optimizing compilers like C2 or Graal or GCC and all these use multiple different versions of compiler graphs. They usually call something like high-level intermediate representation and low-level intermediate representation. So the difference is the high level is high and the low level is low. That's how I explain things. You understand? Okay, that's just a joke. The high level is closer to the source code, right? Again, in our case, Java bytecode, so the nodes in the graph are closer to Java bytecode instructions, while the low-level one is closer to the actual machine instructions for your CPU architecture. It's probably Intel, but could be ARM or Spark or whatever. All right, so we tuned these. Then I have a talk called Twitter's Quest for Holy Grail Runtime, where I basically talk about me working the first year at Twitter and starting to run services on Graal. And what I'm showing in this talk is how much CPU time we're saving by running on Graal instead of C2. And what I also did during this talk was basically what I said you shouldn't be doing. I was hand tuning it because I wanted to see how much can I tune out of it as a human, and this is basically the result. So I'm going to show you 2 slides from my previous talk. We're looking at tweet service. This is 24 hours of tweets, and we're looking at GC cycles. And this is parallel GC. And you see the red and the green one are JDK9, so I did these slides when I thought that JDK9 would be the next Java release, but that was not the case, as we all know. JDK9, the Java no one ever used. So you can see the reduction of GC cycles by just running on Graal, and it's about 2.7%. It's a weird way I put the numbers up there. It's 2.7% reduction in GC cycles by running on Graal instead of C2. And then hand tuning, the 3 parameters I just showed you, I got another 1.5% out of it, which I thought was pretty good, right? It's like almost 50% better than what Graal already gave us. This is the more important one, user CPU time. I care about this one the most because if we can reduce user CPU time, that means we can have less instances to serve the same number of tweet requests in that case, right? And that saves money. So by just running on Graal instead of C2, we save 11% of CPU, which is ridiculous. If you ever worked in the compiler space and you tried some optimizations, 11% is like a lottery win. So, and that means, you remember we have thousands and thousands of instances of the tweet service. This saves a lot of money. It's more than I get paid. I mean, I'm not sure how much you get paid, but it's more than I get paid. Then hand tuning, I got another 2% out of it. And that was like 3 hours on a Friday afternoon. And I was very, very proud of my 2%, and I thought, that's great. But you will see that AUTOTUNE is kicking my ass. So this is just what I did. Then, these are snippets from the configuration file for AUTOTUNE. I gave it ranges. So you don't have to do this, because Bayesian optimization will figure it out anyway, right? But I gave it ranges because I wanted the experiment to be done in a certain amount of time so that I can fit all the graphs beautifully on the slides that I'm going to show you. So we used some ranges here. The test setup, if you're doing performance evaluation, is very, very important. So if you can, use dedicated machines. Because otherwise, if you're running the data center or in the cloud, that would even be worse. You don't even know what else is running on your machine. And if you're expecting performance improvements in the single-digit percentage range, it will always be in the noise. You can never tell if it's actually better or not because of noisy neighbors and crosstalking and all that stuff. So use dedicated machines. And in my case, all the instances that I was running received the exact same requests, tweet requests or whatever. This is very important, not only the same number of requests, but the exact same requests, because in the case of the tweet service, a tweet could be 1 character long or 280. And the memory allocation pattern for the both would be very different. So exact same requests, that version of JVMCI, that version of Graal, not important. Default tiered C1 Graal setup. So who knows what tier compilation is? Right, that's what I thought. So remember when I was talking about C1 and C2? When you run something in the JVM, in Hotspot or OpenJ9 or whatever, you start out interpreting code, and then we compile with C1, as I said, and we compile it in a way that we compile in additional code that collects profiling information. And it collects information like how often was the method called, how often was the loop executed, which if-else branches were taken, what types did we see at call sites. And we use that information, we run a while on the C1 compile code, collect profiling information, and then we recompile with C2 with the collected data, and then we can produce peak performance code. So we're stepping through the tiers. That's what tier compilation is. By default in Hotspot, and that's basically what you're running on, is you run tier compilation C1 and C2. And when you switch on a flag, you basically swap out C2 with Graal. We still compile with C1, but peak performance is produced with Graal. All right, experiment 1, tweet service. My favorite service, it's a Finagle thrift service. Finagle is one of these frameworks that we wrote and open source, so you can get that on GitHub. It's an extensible RPC system for the JVM used to construct high concurrency service. I have no idea what it is. I really have no. I don't need to know. The only thing that's important is it's 92% written in Scala. So most of our services at Twitter are written in Scala, and our stack of most services basically looks like Netty at the bottom, Finagle, and then the logic of the service at the top. That's what they look like. All right. So what's our objective? You can see it at the end. We want to reduce user CPU time, right? And if you remember what Bayesian optimization does, it always looks for a maxima. So, but since we're all very good at computer engineering and are very good at math, we know how to solve that problem, 1 divided by. Amazing. And then the constraint that I'm using, and I'm only using 1, and if we are going to do this, as I said earlier, always on in production, we would have way, way more constraints. Every service owner basically knows what metrics to look at and then what ranges they need to be so that the service is still running fine. We would need to use all of these constraints. But for this example and experiment, I basically used the one, you can see it there, it's throttled, so that Mesos does that to you if you're not a very nice, citizen. Basically, if you use too much CPU or whatever, then you get throttled and you get kicked out. So that's the constraint I used. And that's the run. That's the tweet service, 24 hours of requests per second. You can see the curve, how it goes up and down, how many tweets people send, and then you see the slices. They are 30-minute evaluation runs. 30 minutes is not very long, but it's fine for the tweet service because I know the service really well. I know that everything is being compiled in 30 minutes and it reaches a steady state and we get actually a result that we can trust. And also, I wanted it to finish in 24 hours so I can show it to you. Blue is the experiment, orange is the control. This graph is only to show you they received the same number of requests. And this is basically the outcome, right? This is CPU time. And you see the spikes. That's basically when we restart the JVM, the instance, and the spikes are mostly JIT compilations, right? So we compile for the tweet service, I think we compile roughly 40,000 methods for every instance. And then if the blue line is below the orange one, that's an improvement, right? So this is what you get after the run is done. You get a website, a table, and it's sorted by objective, and the top one is 1.0838. What that means is that we reduced user CPU time by 8.4%, which which is amazing. You remember I got 2, but AUTOTUNE found 8. So that's like 4 times as much. Then we have a 8.2, a 6.4, 6.4, a 5.8. So let's assume the first 2 are outliers, and we could possibly expect an improvement of 6.4-ish%, maybe, I would guess, right? And then on the right, you see the values actually for the parameters, and this is the bottom of the table. And you can see that 3 evaluation runs actually violated the constraint. So we tuned it too far, it didn't work, and it got kicked out. So it actually happens. And then we can look at the charts, as you can see, and the charts look like that. So take these charts with a little bit of grain of salt, because every data point in that chart depends on 2 other values, right? So remember, we're exploring a 3-dimensional space with 3 flags. It's very difficult to visualize that on slides, but at least we see tendencies of what's going on. And you can, if you squint a little, you see certainly a tendency going up. So default of this one was 10, that's where we started. But the value, what it should be, would be 20, 21, 22 in that area, right? This one, maximum inlining size, it's kind of flattish, doesn't seem to affect performance too much. There are 2 outliers on the top right. They might be outliers, they might be not, because remember, they depend on 2 other values that are not the same, so it might just be a perfect configuration, we don't know. And this one is very obvious. Right? The default value for this one was 300, and the best one we have is, what is that, 580 or whatever. So it's basically doubling the value, the default value. What I did next was I ran a verification experiment. So I ran with the top result that AUTOTUNE found. I ran it for 24 hours, the tweet service, and this is the result. So we're comparing C2 and Graal, and then Graal with the AUTOTUNE parameters we just found. This is GC cycles again, parallel GC. And in this particular run, and this was later than the one you saw before, so the code was different, right? In this particular run, we reduced GC cycles by 3.4%, which is, it might not seem much to you, but remember, we're still doing the same amount of work. We just use 3.4% less memory, and remember that GC cycles always affect your latencies. So if you have less GC cycles, your latencies will get better. 3.4. And then this is AUTOTUNE. You can already see, oh yeah, it's a nice improvement. 3.5, up to a total of almost 7. The interesting thing here is, yes, very nice. Graal does a really good job. It optimizes our code nicely. But if we wouldn't be tuning it, we would throw out 100% of the improvement, right? So we doubled it by just tuning it. This is the same data, just visualized differently. It's allocated bytes per tweet. And you can see we basically allocate the same number of bytes per tweet throughout the day. And the improvement is certainly the same, right? Because it reflects in the GC. Okay, 7% less per tweet. User CPU time in this run was 12%. You saw 11 earlier, so that's still the same. And then this is AUTOTUNE, and it gives us another 6.2. Which up to a total of 18%. So the 6.2, if you remember the AUTOTUNE result table, is basically what we expected, right? The first 2 outliers and then a 6.4-ish. That's basically what we are seeing. It's great. 18% less CPU. That means 18% less machines. Imagine how much money that is if you have a lot of machines. Then I looked at P99 latencies as well, because I wanted to see, okay, we are reducing GC and our latency is also improved. I only look at 2 nines and not 3 or 4 nines, because if you look at 3 or 4 nines, you only look at your longest GC, right? So P99 kind of gives you an idea what the real world looks like. We see Graal, certainly better P99 times than C2. A little hard to tell how much it is. This is AUTOTUNE. We can see it's better, but again, hard to tell how much it is. So basically what I did, I integrated over the 24 hours. That's that. And then we can see at the very right what the improvement is. So by just running on Graal instead of C2, we reduce P99 latencies by 20%. It's ridiculous. And then we tune it, we get another 8. So 28% lower P99 latencies. That means If you look on your phone, on your Twitter feed, you get your tweets 28% faster. If you scrolled really fast, you could read 28% more tweets. I would really appreciate that. Would help the stock price, I think. So I did another experiment with a different service called Social Graph. And the reason I'm doing this is because it's also a finagle thrift service, same thing as before. This one is an abstraction for managing many-to-many relationships at Twitter. So it's basically who follows you and who are you following. That's what Social Graph is. And you will see that it depends a lot on the logic of the service, what the improvement looks like. All right? Good. Same thing, objective. We've seen this before. Same constraint. We don't want to get throttled. And here's the run. 30-minute evaluation runs, same thing. Nothing new to see here, really. That's the outcome. So you see, again, there's certainly some experiments where the blue line is way below the orange one. And this is the table. So the best one we have is 7.6%. Very nice. Totally take that. Then there's another 7.6, a 7.2, a 6.8, a 6.4. So if we kind of take what we saw from the tweet service, maybe we can get a 7% improvement for this one. That would be very cool. The bottom of the table looks like that. We had one run that violated the constraint. Don't look at the 3 that are still running. That's a bug. I hope we fixed it since. And that's the chart. It's similar to the tweet service, but not as obvious. There's certainly, again, a tendency up. And then the best one we found is a 23, which is very similar to what we found for the tweet service. And remember, the code stack is pretty much the same. So I'm kind of expecting similar results for both of them. That's the maximum inlining size. There's a slight tendency going upwards. For the tweet service, it was almost flat, but this goes a little bit up. But the best one we found is around 400 because it just paired with the other two better. And then this one, not as obvious as for the tweet service, but certainly a tendency up. And the one thing to point out in this slide is, I'm not sure if you paid attention to the ranges that I gave all the parameters, but for this one, the range was to 650. And I think the best one we found is 649. So I'm assuming if I rerun this experiment with a bigger range or no range, that we might find a better performance result, actually. Good. Same thing. I did a verification experiment. 24 hours of Social Graph, looks like that. And then GC cycles, Social Graph is using CMS, so we're looking at par new cycles here. And we could only reduce GC cycles by 1.6% by running on Graal instead of C2, which, it's still something. It's about half what we got for the tweet service. And then this is AUTOTUNE, and you can already see it in the graph, that it's more than we get out of Graal by default. So if we wouldn't be tuning this one, we would throw out a lot of money out of the window, right? So we tune twice as much as we get by default. And then user CPU time looks like that. 5.5, just by running on Graal. This kind of goes a little bit hand in hand with how much memory we can save, how much can we reduce the GC cycles. We basically reduced GC cycles by half with running on Graal, half of what we got for the tweet service, and it's also pretty much half of the CPU we are saving, right? Tweet service was 12, this is roughly 6, so you see there's certainly a relationship between the two. So this is AUTOTUNE, 7.8. So it's basically what we expected, right? We expected a 7-point-something improvement. We got 7.8. One thing to point out in this slide, if you pay attention, the improvement of the blue and the orange line is pretty much the same. It doesn't matter if the load is low or the load is high. But with the AUTOTUNE result, it's actually better when the load is high. That should not be the case, and I have, unfortunately, no answer for this, and I didn't have time to look into it. But the improvement should be the same. And I picked the one, obviously, over here where it's better, because I want to look good on stage, but also we only care about the improvement when the load is high, right? When the load is low, it doesn't really matter because we have the machines anyway. Okay. Does anyone have a question? This is just a rhetorical question, by the way. You all should have this question, right? Did I do an AUTOTUNE run? Because remember, this is an AUTOTUNE talk, not really a Graal talk, although I talk a lot about Graal. Of course I did, because I cannot come here up on stage and tell you how cool Graal is and the improvements we're getting if I didn't do it with C2 as well. So I tried to pick 3 parameters that are very similar to the ones we were tuning for Graal, and these are the ones. The first one is called max inline level, and Graal doesn't have that. So max inline level, and the default value is 9, is basically how deep inlining goes, how many call levels you go deep. And this is very important in today's world, because you are using 1,000 different frameworks or whatever, and framework A calls framework B and calls C and blah, 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 but at 9 it stops. It's a hard stop in inlining. So you probably never inline the code that you're writing, actually. And we picked 9, I don't even know how long ago. At least 10 years ago, or maybe even more. And the code 10 years ago was very different to the code that we are running today. So if you're thinking about tuning for performance a little bit, try this one. The second one, max inline size, is exactly the same as the one with Graal. It has a very similar name. The difference is the 35 here means bytecode size. You remember for Graal it was nodes in the compiler graph, but here it's bytecode size. And if you ever added assert statements to your code, to a small method or something, and then your performance went to shit, it's because of this guy. Because what happens is if you add assert statements, your bytecode size increases. And C2 doesn't discount for assert statements. I'm very sorry, we never fixed it. It's kind of embarrassing. Use Graal. That's all I can say. Then the last one is inline small code. It's a really odd one. It's 2,000, and 2,000 means native code size. So I wasn't there when this was introduced, but the rationale behind it, I think, was or is, if you want to inline a method and you already have compiled code for it, and it's bigger than 2,000 bytes, it's rather big, right? So let's not inline it. Which is, to some degree, I can agree, but then again, remember what I said earlier, the more you can inline it, actually can reduce your compiler graphs and can reduce your code size because you can collapse more things and remove more things. So it's an odd one, but I tuned it anyway. Okay, same thing, I gave it ranges for the same reasons as before. Then this the run. The C2 run, the tweet service, 30-minute evaluation runs, and this the outcome. We see there's an improvement or sometimes not, and here's the table. So the best one we have is 5.1. And then we have a 3.8, a 3.5, and a 3.3, and a 3. So given what we've seen earlier with Graal, the tweet service, and social graph, probably not 5, right? So let's assume we get a 3.5% improvement if we would do a verification experiment, which I didn't do for C2, by the way. So 3.5 is nice, right? So AUTOTUNE certainly did its job. It tuned a compiler that's been around for 15, 20 years and was tuned to all the code that's out there very heavily, but we can still get another 3.5% out of it. It's great. It's good, but compared to Graal, 18, it's just very different. That's the bottom of the table. No constraint violated. Sure, why not? And here are the charts. So this one, very, very obvious what the hell is going on, right? That's the max inline level that I was talking about. You can see it affects the performance a lot. The default was 9, should be more like 16, 17, 18, and I'm arguing that it should be 18 for all the code out there today. So you might want to increase that if you want to, or move to Graal, that would be even better. This one, max inline size, that one surprised me. Because it's basically the same as the trivial inlining size, where you could see a tendency going up and an improvement. But this is completely flat, right? It doesn't affect performance at all. Yes, there's this one outlier, but that one we said is probably really an outlier. Surprising. And then this one did not surprise me too much. It's the weird one with the 2,000 bytes of native code, doesn't affect performance at all. All right, so that's all I had. The summary of my talk is basically the summary of all of my talks, and it's this one. And the reason I'm showing you this is that's how you turn on Graal in OpenJDK. If you're running on JDK 10 or later, there is, in 9 it also works, but only on Linux, 10 or later, you have Graal in it. You just have to enable it like this. And then you swap out C2 with Graal. If you're running Scala code, you certainly should run on Graal. I've just spoken at Scala Days in Switzerland, and I'm telling you the same that I told them. If you're running Scala code and you're not running on Graal, you're stupid. Because I've never seen Scala code that didn't get a massive improvement by running on Graal. We, at Twitter, I said most of our services are written in Scala, but we have some that are written in Java. And even for the Java ones, we are seeing improvements. So for Java, the situation is this. C2, and I've worked at Sun and Oracle for many years, and not a single day or a single hour or a single minute did we ever tune for any other language than Java. So if you're running something else than Java, Kotlin, Groovy, Clojure, try Graal, absolutely. So the thing is, we tune C2 for Java, so it's very difficult for a new compiler to come in and be better everywhere, right? So we tune C2 for Java, but more importantly, the code you wrote, you tuned it for C2, right? You wrote it in a way that it runs the fastest on C2. So again, very difficult for Graal to just, come in and be better on the code you wrote. The main reason, and I have 3 minutes left, and then it's 3 minutes between you and lunch, so I'm using the 3. I'm doing all these presentations talking about Graal and how much we're saving, and it's really a lot that we're saving. I'm doing it because of a couple reasons. Number one, I'm a very nice person. I want you to save money as well. So if you're going to use Graal and you save 5–10% in CPU, the compute expense of your company is usually a fraction of your revenue, right? So even if your company is small and you only save, I don't know, $1,000 a year or whatever, it's still some money to you, right, if your company is small. And then $1,000 is a very nice Christmas party. And next year when I come back and you are running on Graal and then you come up to me and say, oh, thank you so much, we're saving so much money now, then just buy me a beer or let me sleep at your house. I don't know, whatever. So the other reason is, and that's the real reason, I want Graal to have more exposure. So Graal should be exposed to more code. When you watch the Twitter's Quest for Holy Graal runtime talk, I talk you through all the bugs that we found. But we haven't found a bug in over 2 years. And I haven't mentioned this yet, the tweet service, the social graph service, and a bunch of other services, 20, 30 services, run today 100% on Graal in production. So every tweet you've seen in the last 2 years was served to you by code compiled by Graal. And have you lost any tweets? I did not. You would even know if you lost one, but I tell you, you have not. So please, please, please run your pet project or even at your company in production. Go to work on Monday and just turn it on. Exactly, yeah, these two are already, I'm going in on the weekend. Because we need your shitty production code to be run on Graal. We need these corner cases. We need to find the bugs that are still hiding somewhere. And I want this because of selfish reasons, because if you find the bug, we don't find it. And if Twitter would be down, everyone would be very sad, including me. And I would be the saddest person because then I have to fix it. So try it out. I'm promising you will see, no, I'm not promising that. If you run on Scala, I'm promising you will see an improvement. With Java, it's like a 50-50 chance if it's better or not. So give it a shot. If it's better for you, let us know, right? Tweet it out or whatever, or post it on Facebook or Instagram, I don't care. Just let us know that it works better for you. Would be very interesting. If it crashes, perfect. That's exactly what I want. You found a bug. file a bug on GitHub. Oracle Labs or us or whoever will try to fix it. If it runs worse for you, slower or whatever, also let us know, right? Because we want to know about the situations where Graal is not as good as C2 yet. Might be difficult if it's proprietary code at your company, but maybe you can extract a small test case or something and send it to us. That's really all I had. And tweet about everything, the event and Krakow. Thank you very much.